Thanks everybody for coming. This is a lecture entitled Siletzia Fireworks in the Pacific Northwest. Now let me explain. Pacific Northwest, that's us, Ellensburg, Washington, that's where you're seated right now. Great. Siletzia, some of you have heard of, but I need to elaborate. And fireworks, that could mean about anything. And so I need to define that as well. But there is a gimmick, there is a plan, and it involves not so much Siletzia itself, but the fireworks, the effects, the after effects, the result of adding a huge exotic terrain. The last one to come in, Siletzia, which was a major land grab for the Pacific Northwest. And many of those fireworks, whatever they happen to be, are right here in the Pacific Northwest. And you know many of those places. You just didn't plug it into this regional story. So that is the plan tonight. It's going to get fancy, but I think we should start with something very simple. Do you mind? Something very simple, nice, and tidy from Geology 101 land. He goes to a map of the Pacific Northwest, right here. Here we are in Ellensburg. Eastern Washington is separated from Western Washington by a mountain range called the Cascades. It's not just Washington. That Cascade Curtain, as it's called culturally, is a geologic entity. It's where our beautiful, famous stratovolcanoes in the Pacific Northwest reside. And there's all sorts of stratovolcanoes lined up in this beautiful line. Yes, I'm talking about Rainier and St. Helens and Adams and Baker and Glacier Peak, and down here in California, Lassen and Shasta. If you want to do Oregon, we can do Hood and Three Sisters and Crater Lake. Okay, this is pretty basic. And this is nice and tidy, the Cascade Volcanic Arc. Why does it exist? There's an oceanic trench offshore. There's an oceanic plate in its most simple way in Geology 101 land that's moving west to east. It's called the Juan de Fuca Plate. And as long as we have subduction of the Juan de Fuca Plate, we're generating magmas into this Cascade Volcanic Arc. We're good. The Cascade Arc is younger than 44 million years old. So in other words, we've had this line of stratovolcanoes for 44 million years. And I do not mean that Mount Rainier has been standing for 44 million years. Instead, I mean that there has been stratovolcano eruptions for 44 million years. Each individual cone lives for about 2 million years before it goes away. So there's all sorts of ghost volcanoes in this line. But we're still in a nice tidy line of volcanoes. That's not the topic tonight. And Siletzia was a volcano, but Siletzia is not one of these volcanoes in the Cascades. And so for the first time tonight, we introduced the idea that we have to go older than 44 million years ago. And generally, we need to go east of the Cascades. That's us. You are here. And we want to look for volcanoes and other things that are east of the Cascades that are older than 44 million years ago. And our number tonight, I guess our two numbers tonight, entire lecture tonight is confined between 55 million years ago and 44 million years ago. That's our time window tonight. Siletzia and its fireworks. We still don't know what that is, but that's the story. Okay? Well, what was Siletzia? Well, it was a huge oceanic plateau. Oceanic plateau. It was a volcano out in the water. It was out here. And it was a monster oceanic plateau. It was an incredible pile of flood basalt that was built quickly 55 million years ago. So you're like, I'm already confused. I thought we were going to look to the east of the Cascades, and now you're out in the water. Well, there's a relationship. Be patient with me, please. So the formation of Siletzia off the coast of the Pacific Northwest 55 million years ago was an incredible pile of flood basalts, mostly underwater, but occasionally it did get high enough to get out of the water and it'd actually be an island. And you're like, wow, really? We used to have an island off the coast of southern Oregon and northern California? Yes. Well, we don't have it anymore. It's not out there anymore. You would have heard about it probably. So what happened to it? It got added. to the edge of the Pacific Northwest. It's the last exotic terrain to add. The volume of this flood basalt in Siletzia was huge. I've already said that, but how huge is huge? Well, we do have flood basalts here in the desert, and they're still here. They're way younger than 44 million years ago. They're 16 million years old. That's the German chocolate cake, the Columbia River basalts, 3 miles thick. If you drill through those flood basalts, those Miocene, 16 million year old continental flood basalts here. But if we go out to the Siletzia story, that's 17 cakes. That's 17 times the volume of our flood basalts. It was a monster. 17 times the volume of basaltic material created pretty quickly 55 million years ago out in the water. Well, if it's not out there anymore, and it's 17 times the volume of our normal German chocolate cake, we should be able to find it then, right? That's a lot of basalt. Yes. Everything west of the Cascades on this map is mostly Siletzia basalt. Not all, but most. The surface and the subsurface, there's a lot of Siletzia that used to be out here and got added. It got added 50 million years ago. Keeping up with the dates? 55, we make the thing. 50 million years ago, we add it. Either with North America drifting out to it, or Siletzia being sent towards us, or maybe a combination of both. Doesn't even matter, it's here. But if that still doesn't seem right, that this acreage, is this right here, more than 17 times the volume of the German chocolate cake in eastern Washington, does this help? When Siletzia got added 50 million years ago, it was all here, the oceanic plateau. But shortly after it docked, it broke in half, and the western half of that oceanic plateau started heading north. And it's still heading north today. It's up in southeast Alaska, and it is still subducting and accreting to southwest Alaska, southeast Alaska, southern Alaska. That's the Yakutat terrain. So there's the missing half of this giant oceanic plateau. So in a way, I'm done talking about Siletzia itself, half here and half up in Alaska. That's not the focus. The focus are the fireworks. But I hope you get the sense of this now, that the size of this thing was enormous, and so the effect of adding such large material to our map, it's not just going to kiss the shore. It's going to plow in. It's going to create all sorts of problems or fireworks or excitement. What might those look like? And where can you go find some of those guys? Oh my God, the energy is so great in the room. Like, I don't know if you've ever taught in a room before, but like, it's like a vibrating silence as opposed to a silence. It's a good silence. So thank you. All right. No, I'm going to keep this. You know what? I'm going to keep this. Improvisation number 4 already. Let me just use some colored chalk and verbally, while I'm drawing, give you a sense of the fireworks that don't make any sense if we just think of volcanoes being a line like we do with the Cascades. So now I am talking about fireworks between 55 and 44 million years ago. Ready? Here we go. Oh, we got magmas. Uh-oh. What's this? We have plutons between 55 and 44 million years ago. I'm kind of exaggerating, but not really. Some of them are beneath the German chocolate cake today, but just play along with me if you like. These are granites. These are high silica plutonic rocks, magma chamber rocks. And there are occasionally some volcanic remains from those old systems, but these are Eocene plutons, red. Blue chalk, I'm going to make some blue kind of squarish things. These aren't magmas. These are metamorphic core complexes. These are places where metamorphic rock was at 20 kilometers depth, high temperatures and high pressures, And then, I don't know, between 55 and 44 million years ago, this metamorphic rock starts rising quickly and coming to the surface. It shouldn't be up here. It should be way down. But a geologic elevator brought it up. That's what each of these blue squares represent. These are the fireworks. I'm going to explain why I'm using the phrase fireworks in just a second. I got another color chalk. I got orange. I'll use green. Oh boy. Messy. Going to have the stage full of chalk here. In the middle of all of this, the red magmas and the blue squared metamorphic core complexes, these turtles rising with these slippery shells and having these upper plates sliding away, there are places where there are sand boxes, sedimentary basins with floors that are dropping out. So the blue are rising areas. The green dotted areas are places where the floor is dropping. So we have this going on at the same time. These are sandstone basins, essentially, deep sandstone basins with some volcanic ash tephras recording some old volcanic events. And finally, this is orange. I don't know if it looks like orange to you. There are faults, strike-slip faults, and each of these faults has motion to the northwest on the west side of the fault. Each strike-slip fault is doing this and generating earthquakes. None of these things were here before Siletzia arrived. These are the Siletzia fireworks. It's not Siletzia, it's the fireworks that have responded to that impact. Why am I saying fireworks? Well, you've been to a fireworks show. What's the experience? It's dark. Is it dark enough? Are they going to start? Is it dark enough? When are they going to start? And then the men over in the parking lot. There's a 1-2 punch. There's set the firework off in the parking lot, and then the firework happens. Different colors. The foo is Siletzia arriving. And roughly at the same time and slightly delayed after is all of this stuff going on inland. But it's not in a line. This isn't a volcanic arc. This isn't a subduction story. This isn't a simple ocean plate diving. How do we explain all this stuff? And if you're getting a little impatient, these are things like the Liberty Gold just north of Ellensburg, the Teanaway feeder dikes, the Golden Horn batholith up in the North Cascades, the granite of Grand Coulee Dam, the Kamloops magmas, the Ross Lake Fault Zone, the Leavenworth Fault Zone, the metamorphic core complexes up in the Shuswap, the North Cascades Highway, the uplift there. These are places we know, but typically are presented in little bite-sized nuggets, a little factoid here, a little factoid there. I'm not into that. I'm into regional stories, and I get particularly charged if I can take something local and put it into something big, especially if there's questions about why it all happened and tectonic models that we might have, and we do. I wouldn't waste your time if we wouldn't have a tectonic model. Okay, let's do this. I think I'm going to pick up the pace now after bumping my microphone and give you a little bit more visuals, but I want this to be fast. So the red splotches are plutons, okay? And we don't know why they're coming up, and we know that there's a lot of them, and they stretch all the way back to Wyoming. They stretch all the way back to the Dakotas. This is not just Washington. But I want to do this in side profile. So here comes our magma. Down below, it's hot. Why is it forming? Question mark. We're going to try to address, especially with the visuals. We'll get that magma to the surface, and I would love to draw you Mount Rainier right now, but I'm not going to. Because the chemistry of these magmas and other indicators, by the way, most of these magmas, most of these red blotches have gold and silver associated with them. Gold and silver. Why? Still don't know that answer. But many of the gold and silver deposits in the Pacific Northwest are tied to this swarm of Siletzia fireworks. What I want to draw for you is this. Aren't you glad you came? I don't want to draw a cone. I don't want to draw a shield volcano. I want to draw a bimodal volcanism system. I want to draw a supervolcanic explosion creating rhyolite, and I want to have effusive basalt coming out at the same time. Bimodal, two different opposite types of lavas coming out of the ground in the same system. That is the general story with much of this story here in these volcanic centers. Supervolcano scenes. Much more work needs to be done on that, but for instance, the Golden Horn batholith up in the North Cascades produced a bunch of volcanic ash. Mike Eddy and Aaron Donaghy think they have those ashes in the Chumstick Basin right over by Leavenworth. They have precise timing matches between the magma and the deposits from more than 45 million years ago. Pretty impressive. And I think it's just the start. I think there's going to be a lot more detailed geochronology work with these Eocene magmas and these Eocene volcanic deposits to put that together. But I said it was going to be quick. Let's keep that on the board. Where's Bijou? Here. The blue are the places where we have a geologic elevator going up. And when I was in graduate school in the 1980s, this was the hot topic, these metamorphic core complexes and these detachment faults. And the idea is that you have metamorphic rock that should be down deep with a brittle overplate or upper plate that's going to be slid away. And so these blue things are the result of major uplift. Why? Why is this uplift happening so quickly at each of those blue squares? The Valhalla, the Shuswap, there's one in Republic. All of these places where we're sliding the upper plate away, sedimentary rock, and we're lifting this slippery metamorphic material. When you drive North Cascades Highway, the next time, you're driving right through one of these metamorphic core complexes. The Skagit gneiss, the Squacain gneiss, the Chelan migmatite by Lake Chelan. That's what we're talking about. And that's just one of many of these. Is the lecture working for you? I hope that you're not only kind of following here, but you're like, why? There must be some sort of explanation for this. Well, there's attempts. It's coming. A model is coming. Doesn't have to be the right model, but some models have been published recently. This is all brand new work. What color was the sand? Right, green. Green. So, at the same time we're doing this geologic lifting, we're also dropping the floor of these sedimentary basins. Most famously, for me, the one that's been studied to death, and I'm pointing over to Highway 2 between Wenatchee and Leavenworth. That's the Chumstick Sedimentary Basin. The Shastan Pinnacles, all those beautiful sandstone outcroppings, that's what I'm talking about. And yes, within the Chumstick are these tuffs. I've made some videos on them. And those tuffs, at least one of them, maybe more than one of them, are coming from known volcanic centers during this time. Pretty close to home. But the boundary, I don't even know what color I used. Oh, orange. The boundary are the strike-slip faults. So instead of these sedimentary basins being in a true sandbox where you're just pulling the crust open and all this sand is coming in from the uplifting elevators on opposite side, we need to add the idea that these sedimentary basins, these sandboxes, are bounded by strike-slip faults, and we are wrenching the crust like this. We're still opening it. This is called transtension. And I'm laying all this out in detail so that our model is going to come in and save the day and explain why all of this is happening at the same time. But we're opening, torquing the crust, and all this sediment is falling in. And there are many of these arcosic sandstone sedimentary basins throughout the region. Okay, we know Siletzia, we know the fireworks. Can we get to a model, please? I can try a little bit with the chalkboards, but I think the visuals are really going to do the work for us. So, the germ of this lecture came in 2019. And I went to a geology conference in Portland, a GSA sectional meeting. And there was a geologist named Jeff Tepper who was standing at a poster. And that's one way to present your new scientific work. And I will always remember that session, and I never left. Usually when you visit a poster, you make some chit-chat, and you kind of pretend like you're reading some text, and then you move on. But I was just like, reading just, I hogged the thing for like an hour and a half. I think Jeff's like, get this guy out of here. But he was talking about my state, and Jeff Tepper has a long teaching history at University of Puget Sound in Tacoma. And over the last 25 years, Jeff Tepper has taken seniors, undergraduate students, and taken them to different Eocene plutons and lava flows, and they've sampled and they've gone back to the lab and they've gotten high precision geochemistry and high precision uranium-lead dates. And so really in the last generation, mainly through Jeff Tepper's work, each of these Eocene plutons have been studied very carefully, that there was an age progression. That there was an age progression of these plutons, and therefore of these volcanoes as well. This ain't no cascade arc. We don't have a line. We have an age progression, that these plutons are forming 52 million years old, and that we're having potentially supervolcanic explosions up in the Panhandle of Idaho. There's a thought. And then 51, 50, 49, 48, 47, 46, 45, 44, we're sweeping. Somehow we're having some igneous activity sweeping in a weird direction. And this must have something to do with Siletzia. Do you have an idea? Like, how would you explain this? And if these are not subduction zone magmas, which they are clearly not, geochemically and otherwise, why are we even getting magmas coming to the surface? Well, I'll give you a teaser right now. The geochem says that these are mantle-derived magmas, that hot mantle is surging to the surface faster and quicker and more efficiently than they should. And they're heating up the crust a lot faster. There's a deeper hot mantle source that's just accelerating the mantle, accelerating the melting, and we're getting this weird pattern. Now, there's not an obvious plate tectonic model that comes to mind to ultimately explain this, let alone this, and this is like a four-ring circus going on simultaneously. How you're supposed to come up with one plate tectonic explanation for all of it? Well, I don't know. Maybe I'm building it up too much. Maybe I'll share the model and you're like, I don't think I even see it. And that might very well be true. But the data is there now, and it's up to as many geologists as possible to weigh in on this story. I'm going to just try this verbally, and then I think we are switching to the slides. But I'm going to try to do the... No, I'm going to do it this way. I'm not going to do it verbally. Are you kidding me? I'm not doing it verbally. Here is the tectonic model. Keep all these on the board. I'm just going to stay over here. Hope that's okay. Here goes nothing. What happens if instead of a big tectonic plate that's subducting, like we had with the Cascades, what if instead we take a spreading ridge, a spreading center, like the Mid-Atlantic Ridge, but we're in the East Pacific Rise, we're in the East Pacific Ocean at this time we're talking about tonight. And what happens if you subduct a ridge? What happens if you subduct a divergent plate boundary? What does that look like? It's basically a place where hot mantle is coming up and generating new seafloor crust. But what happens if you have a continent encroach that scene? And I don't know. Excuse me. Oh, God. Mike, I got to get the mop after this. And what happens if you have an oceanic plateau? Did you forget about it? Straddling that seafloor spreading center. Instead of that oceanic plateau out in the middle of an ocean plate, that's maybe what you were thinking, I'm not sure. What if half of the oceanic plateau was on one ocean plate going this direction? We lost our arrows. And what happened if the other side is on another plate? It's straddling two oceanic plates. And what happens if North America then starts encroaching into the whole scene? Is it possible that the North American continent, as it encroaches on top of that seafloor spreading center, is some sort of slab window where up here we still have an ocean plate and it's subducting beneath British Columbia between 55 and 45 million years ago, right? We're not talking about today, we're talking about back then, the Eocene. And maybe down here we still have an ocean plate being generated, and that's subducting nicely to the south. But what happens in here? We're subducting nothing. We're subducting the boundary, and possibly that slab window, that place where we're not subducting an actual plate, is basically a big old hole where we can get hot mantle, shallower levels than we would otherwise expect. And if I then take my red colors, does that help us see why the Tianaway lavas and many other lavas in this window work with this pattern? You're like, maybe, but like, how does that explain the geologic elevator going up? I'll wait for that. How does that explain the strike-slip faults? How does that explain the sedimentary basins? Well, give the slides a chance. But this kind of going back and forth between detailed field data and big picture thinking is, to me, some of the funnest geology that we have. It's not just taking a local story, it's thinking regionally, and especially at a time when 30 years ago I was taught about the Challis magmas when I went to school in Pocatello, but they were called the Challis Arc. And it was assumed that those magmas of the Idaho batholith that were of this age, not all the Idaho batholith is this age, but some of it is, Eocene age, and the Absaricas, and many of these other Eocene magmas, I was taught that they were subduction generated. And maybe some are still thinking that. But this kind of new data and this kind of synthesis of all these different kinds of things help us see that this is a regional story that is not a subduction story. If you want a subduction story, it's a subduction of a boundary as opposed to a subduction of a plate. That's my best attempt, but I got one more thing I want to do before we go to the slides. You're waiting, I think, for why we go 52, aren't you? to 44. Be nice if the model suggested that. And this is Jeff Tepper's model, the guy standing at the poster trying to get rid of me. He wasn't. He was very, I knew him before, and so it was nice. Tried not to hog the time. This model is promising to me. We'll see how long it lasts, but it's been published now, and so I'm happy to share it with you. He has a slab rollback model. And so Jeff says, yeah, there's maybe a spreading ridge out there. Yeah, there's Siletzia out there for sure. And the impact of Siletzia with North America is definitely part of this story. He's talking to us now through his scientific paper. But Jeff says, I think I have an idea that maybe tomography can support, in other words, looking for slabs that are down below. And Jeff says, what if this was all part of the same big oceanic plate? And what if we break the plate? What if we break it off from the rest of the subducted ocean plate about 55 million years ago under Montana? And how about the oceanic plate between these two blue lines starts to sag, starts to go down towards hell? And to do that, we need to not only break it away from the rest of this monster plate under Montana, but we need to tear it up here at the Canadian border and down here at the, I should have this line down here at the Oregon-California line. And Jeff says, now just follow me here if you can follow this, to explain this 52 to 44 age progression, we have hot mantle under the plate. My blue arms now are the oceanic plate, okay? You're looking side view with me, but you're looking map view on the map. That's convenient, map view on the map. Break the plate in Montana 55 million years ago. Tear it on both sides. Break it free. That's over here and that's over here. There's hot mantle under my arms, but how are we going to get the hot mantle to the surface? We roll the plate down, and what's coming around my fingertips? Hot mantle. Hot mantle is coming up around my fingertips, 52 in the panhandle of Idaho, 51, 50, 49, 48, 47. In other words, we have an age progression of these magmas as we continue to lower the drawbridge and allow the hot mantle to generate melts working northeast to southwest. You kind of seeing it? Hope so. And if you want a crescendo, we're going to break the frickin' thing again at 50 million years ago. So this thing that is not only broken once to start rolling back, breaks again. Somebody, Patrick, get a saw. Cut my biceps, please. We'll now have this thing fall because there's a whole generation of magmas, bimodal volcanic magmas in central Washington, including the Teanaway basalts, rhyolites and basalts, that appear to be from this second breakoff. Let's see if these visuals can help. I'm confident that they can. Not only with the models, with other things. Well, let's start simply, just like we were at the beginning of our talk today. This is not our Siletzia story. This is our well-behaved, simple oceanic versus continental plate boundary to create the Cascade volcanic arc. And we can take this picture and go back 44 million years. Jeff Tepper is confident that the beginning of our known Cascade volcanic arc, 44, that's the magic number. But tonight we are earlier than 44 million years ago. Well, here's Tanya Atwater, Santa Barbara, and she's showing us what? Well, she's showing us a subducting spreading ridge. That's encouraging. And this is on a loop. And this, I think this animation is 20 years old at least, maybe 30, I don't know. But with her expertise in reconstructing ocean plates in the Pacific Basin, and she's the expert on that, she's one of the most famous geologists we have, she's showing this subducting spreading ridge. So Jeff Tepper didn't dream it up. There's many geologists who've come up with this concept. Okay, well, what did you have in mind from the chalkboard? Is this kind of what you had in mind? This is a classic picture of a slab window when you subduct a spreading ridge underneath a continent. And the wider you get this gap, the more you're getting our Eocene-like magmas, our fireworks magmas that we've been talking about today. Another diagram showing the same thing. Slab window, maybe a new concept to most here tonight. It's an interesting concept, and perhaps we have a classic example of it in the Eocene here in the Pacific Northwest. Okay, we get it. There's a third one, my God. All right, but yes, now we're talking about the fact that we're leaking this hot mantle up through that window. All right, well, we're feeling comfortable. Hopefully now we can make sense of maps like this. So this is roughly 50 million years ago when we docked the oceanic plateau. Half of it's Siletzia, stays with us. The other half is Yakutat, and it's about to make its journey to the north. And if you're curious about that story, I think that's another lecture coming. This very bright student, Erin Donaghy, who I've been making videos with over the last few years, she's a student of Michael Eddy at Purdue University. That's her PhD dissertation, matching geology from Siletzia with the geology of Yakutat. She's been hop, skipping, and jumping between Southeast Alaska and the Olympic Peninsula to make those cases. So I'm particularly excited to follow through on that. But for now, we just need cartoons like this until Erin finishes her work. Where can I find the Siletzia bedrock? Well, you can find it in Roseburg, Oregon, and Corvallis, and Siletz River, and Tillamook. All those colors in red, all those colors in blue, they're all part of this greater Siletzia. And the places where we don't have bright colors is where Siletzia is in the subsurface. There's a lot of basalt that was originally offshore. Today, Hurricane Ridge Road is a nice classic place to visit that Siletzia basalt, including pillows within it. But I like this diagram from Robert Hildebrand saying if you go west of Seattle, that's the Siletzia accretion story. If you go east of Siletzia, here's the fireworks, and just a portion of it. The North Cascades, and this is a new way to think of the North Cascades probably, is a showcase for Eocene fireworks. Eocene effects of the Siletzia accretion. Okay, we're pros now. I think we've got it. And you'll notice tonight I have backed off of the Yellowstone hotspot story. And I did that 5, 6, 7 years ago in one of these downtown events. It was a lecture called Yellowstone Hotspot and Liberty Gold. I think that was the title. And there's still thought about the Yellowstone mantle plume creating Siletzia, and then North America drifting over the top of that mantle plume, and it's now in Wyoming. But I'm choosing to go a completely different angle here tonight. What is new to us tonight are concepts like this. So let's say that's Siletzia offshore, our oceanic plateau, and let's say it is being brought into us. That's fine. What happens when you first dock such a monster oceanic plate? The thought is you clog the trench. It's too big to just go down the tubes. And so we're going to take our ocean crust that was subducted, which used to be between Siletzia and the coast, and we're going to tear it, and we're going to break it. That's what Tepper was talking about, right? So if you were missing the connection between Siletzia docking and all of this crazy stuff, maybe you're starting to see it with some of these cartoons. So this is India colliding with Asia, also courtesy of Atwater. But I just want to show you how, again, if we close an ocean basin between two massive pieces of crust, we're going to snap off that ocean plate. We're going to tear it. We're going to fail it. We're going to cut it off, and we're going to get hot mantle to surge to the surface. This is slab failure, essentially. We're not rolling back in here. That's the only thing we would need if we want to show this as truly Siletzia with Jeff Tepper's model. But otherwise, I like it to show us about failing that ocean slab. Here's Jenda Johnson doing an animation with Anita Grunder, and a portion of it showing Siletzia docking. Let's keep our eye on this oceanic plate. Uh-oh, there we go. We're going to fail it. We're going to have it break off. And we're not showing here, but we could. A bunch of magmas coming up. And we could also show the rollback, which again is Tepper's idea, not necessarily from this animation. This is on a loop, of course. Please notice that the position of the trench is going to suddenly shift west because we're adding this huge gumdrop, this huge chocolate gumdrop. Right there. And what do? We set up the Cascade Arc at 44. We're starting with all these animations like we were just doing with the chalkboards. So I thought I'd just kind of get us to these animations quickly as opposed to forgetting about them. This one's maybe less sexy to look at, but there's a lot of good stuff in it. This is from Ray Wells, who was really the godfather of thinking about all things Siletzia and did much of the work. I'll play it and try to narrate. This starts 55 million years ago. The capital S is Siletzia. The capital Y is Yakutat. That's the one that's going to go up to Alaska. Ray has different ages of ocean crust in this kind of herky-jerky animation. And he's also emphasizing the Yellowstone hotspot, which today is, let's get it there. Yeah, okay, good. Back up. So he's got a fixed Yellowstone hotspot creating this oceanic plateau out in the water. And then North America is going to cross over the top of it, and that same Yellowstone mantle plume is going to be in Wyoming. But more apropos for us tonight, that's French, is we have two different shades of green. And I think what Ray is showing us is that the light green is when we have these things on the move, and when they're dark green, they're a moose on our windshield. And so the light green, there's the Yakutat doing its northward journey that's the western half of this massive oceanic plateau. We'll do it one more time. You're probably noticing a bunch of stuff that I'm not noticing. And you might notice that Ray, for whatever reason, doesn't want Siletzia and Yakutat as one big hunk, like is pleasing to me. And then we cut it in half. We will see what the new researchers decide they want to do. But again, that's mostly Michael Eddy and Aaron Donaghy from Purdue University. Keep your eyes open for their work coming in the next 5 years. Well, this is not the first time this has happened, that we've run into one of these massive oceanic plateaus. If we go back 170 million years ago, there was an oceanic plateau that had Cache Creek limestones on top of it. That got added and cut in half, dock and slice. If we jump to 100 million years ago, there's the Carmoutzen flood basalts that make up a majority of the Vancouver Island area, part of Wrangellia. That was docked and sliced. So this is a repeat offender. Many of these geologic chapters are not brand new. It's kind of fun to see multiple generations of this story. So yes, tonight we're only focusing on 50 million years ago and the last major collision, but we had two other major collisions that severely impact the geology of Washington. And that means that if you go to the North Cascades and start looking at granites, they're of different generations and they tell of different collisional stories. And I'm not saying that all those granites are from slab failure and extension like we're talking about tonight, but I am saying that the Eocene ones are. If you know the Railroad Creek Pluton, the Duncan Hill Pluton, the Golden Horn Pluton, and the Cooper Mountain Pluton, those are all Eocene plutons that are beautifully in our slab window and not subduction-generated magmas. And by the way, you need extension during that. And the metamorphic core complexes are also a direct result of massive amounts of crustal extension. But if we go back to the earliest generations of magmas exposed in the North Cascades, that's not an Eocene story. That's not a slab window story. Mount Stewart, Black Peak, 10 Peak, 6-finger jack, 7-finger jack, those are granites that have paleomag telling us that they came from the south. Remember that? So to get some photos from Backcountry Gary Paul from the North Cascades, it boils down to some simple approaches. Oh, Eocene. Oh, the slab window. Gold and silver may be tied to this. Oh, Black Peak, twice as old. Totally different chapter, totally different story. That's what some of us can do now with enough geology background to get a little bit more out of these mountain scenes. And these places that have granites that are right up next to each other are not the same age, not the same chemistry, and not the same story. This is my favorite photograph of the Golden Horn batholith. Liberty Bell, if you know it better that way. Washington Pass, one of my favorite areas in Washington. Thank you, Gary, for the photographs. And Mike Eddy, again, part of this research team, is starting to see that the Golden Horn, which is massive in volume, is almost all exactly the same age. And so one of his angles is, how do you create incredible flare-up of magma at the snap of a geologic finger? And to him, the Golden Horn is one of the best places to study this very quick magma generation story. More coming on that from him. In this photograph from Gary Paul, we have the Golden Horn, which I just got done talking about, the Ross Lake, which is an initiated strike-slip fault at the same time, and in the background, the Skagit Gneiss, one of our geologic elevators coming up. So 3 of the 4 in the 4-ring circus are in this photograph. And it doesn't hurt that it's a beautiful area besides. So thanks to these 3 geologists who 4 years ago got a major National Science Foundation grant and asked me to be their public outreach person. And so they've been the motivator for me to make videos and to learn what I've done. And much of the learning I've done with you on the internet has been spurred by the work of these 3. Plus our buddy Jeff Tepper, who we haven't gotten to, but we are almost to him. Couple quick photos from the geologic elevator. The concept of the North Cascades. This is a Darrell Cowan slide. This orange is just so weird. It's like a black hole. It doesn't match the geology both to the east and the west of the North Cascades in Washington. Why is it orange? That's the place that popped up suddenly as a metamorphic core complex. And all of those volcanoes are gone. Probably a bunch of the plutonic rock is gone. It eroded away as this thing rocketed to the surface. Skagit Gneiss, Swakane Gneiss, Chelan Migmatite. The metamorphic core complexes themselves. The biggest one is up in British Columbia, the Shuswap. Entire mountain ranges are part of these elevators going up. It's hard to grasp the scale of much of this. But then the fact that it repeats and repeats and repeats in that wedge, that slab window, really fun to plug it all into something bigger. These are photos from backcountry Eric Kolb up in British Columbia. Metamorphic core complexes, metamorphic rocks, high temperature, high pressure metamorphic rocks that have no business being up here. They should be way down. There's a map of the Shuswap crossing down into northern Washington. All right, we got it. From many of these scientific papers, Bob Miller and friends, they're plotting with beautiful colors between 60 and 40 million years ago, all of this happening simultaneously. So you need high precision dating techniques to keep track of things. And so as an example is looking at folds inland from the impact of Siletzia. The Swak Formation north of Ellensburg is intentionally folded as a direct result of docking Siletzia. But these grabens as well, these downgrab, this is the only photo I think I have of a sedimentary basin with a strike-slip fault on both sides. We're looking south. There's a friend, Mount Stewart. You're sitting in an auditorium just on the other side of that skyline. So Wenatchee's off to our left, but those sandboxes, those Chewacum sandboxes, would not be there without this idea. Oh, this is the chumstick, sorry. Skip it. Skip it. We don't need it. Even the Straight Creek Fault got started as Siletzia accreted. You've heard it now, but I'm trying to fill in a bunch of details to help you see. So you look at a map of Washington like this, looks familiar, but think of all the geologic stories that are hidden in all those different shades. And these stories are brand new, from work that's been done in the last decade. We're going to finish tonight with where this lecture got started. Pre-COVID, I was all set to go with this lecture, and I had this auditorium booked in April of 2020. Didn't happen. So here we are 3 years later, finally getting a chance to share it with you. All spurred on by the work by Dr. Jeff Tepper, University of Puget Sound. That was the poster where I hugged all the time. And here are some of the maps from his original thought. I just couldn't believe that he had a chance to survey all those red areas, fireworks of volcanic rock, yellow, deep yellow, Eocene volcanics. You see the Republic area is chock full of stuff. And then the pale yellow is the Cascade Volcanic Arc, which is too young for our story tonight. Jeff and many others are working with zircons that they pull out of these volcanic rocks and plutonic rocks to get very high precision dates. And Reed Lewis over in Idaho sent this one to me just on his own using some colored pencils, showed that these Eocene igneous rocks, both volcanic in orange and plutonic in red, are all through Idaho, Montana, and Wyoming as well. It's not just a Washington story. So I broke out the little colored pencils back in early 2020, getting ready for this auditorium back then, and just said, where can I intersect places in Washington that at least I vaguely know with these places that are yielding these stories? So I switched from red to blue for some reason. And there's the flood basalts covering up much of this. The German chocolate cake is in the way of what we want to do here tonight. But this is Saddle Rock, looming above Wenatchee. And when Tepper, after that poster session, says, well, it's COVID, but I want to get out and sample a few more rocks. Have you got an idea? I said, have you been to Wenatchee? Not much. So I started coloring little cartoons of the plutons that I knew about, looming above Wenatchee, Washington, and said maybe he'd want to come over and sample. So he did, just he and I. And he collected some samples from Saddle Rock and Castle Rock and other places, Wenatchee Dome, all right near Wenatchee, Washington. And he added them to his collection of Eocene plutons. And his ages from all those locations in Wenatchee, 44 million years old, right at the end of the slab rollback and right at the beginning of the Cascade Volcanic Arc story. So these familiar places in Wenatchee are the latest addition to his field data set. Some of these break-off rocks not only go in the Teanaway area, but they head through the Cascades, and you can even find some of these things on western Washington. Mount Pilchuck, Bald Mountain, Mount Persis. They have the right age to go along with the Teanaway field feeder dikes and the Teanaway story just north of Ellensburg. So the intersection of this rollback story of the oceanic plate intersecting with the setting up of the earliest days of the Cascade Arc, pretty fun, about 44 million years ago. So here's some backcountry Gary photos from western Washington near his house in Darrington that feed into this story tonight. So not all these granites have the same stories to tell. I think you knew that before you walked in this auditorium. Some final brand new maps. I talked to Jeff Tepper this morning and I said, I got a few hours. I got to get this thing ready for tonight. And he said, okay, well, we just got this paper published. Let me send you a few finished figures. So this is a brand new figure coming from a paper that's coming out this year, has not come out yet. A little bit more professional look at the Absaricas, the Chalice, the Montana Alkalic Province, the Kamloops magmas up in British Columbia, all part of this story. And here are these brand new maps from Jeff Tepper showing his sample sites in northeastern Washington. Not all of them Eocene, but the Eocene ones yielded the rollback story, the age progression, the northeast to southwest progression. Early maps from his poster, more professional maps that have come out in the last year. 52, 51, working their way from northeast to southwest, young to the southwest, indicating to him the leading edge of my arms drooping and the hot mantle rising around my fingers. To finish, put it all together, Jeff Tepper says, here's his visualization. I don't know if it's yours. Siletzia coming in, filling the Columbia embayment, spreading ridge offset by transformed faults. And a slab curtain is tomography that we do have of a plate that's hanging vertically beneath Idaho. So the idea of breaking the plate is not just an idea. There is seismic tomography data underneath the Pacific Northwest to show. And the green striped area is a tear. It's an opening where the hot mantle can surge to the surface. You want it again? Block diagram, same idea. Spreading ridge subducting beneath Washington and Oregon, dock Siletzia, break the slab once, break it again, roll the plate down, almost like a tablecloth, having its own momentum falling off the edge of your grandmother's table. And a brand new figure that I haven't even looked at very carefully yet because it was sent to me 3 hours ago. But this Southern Cascadia slab, Northern Cascadia slab, Spencer Fuston from Houston and others have found these broken slabs down below. And Jeff is encouraged that it matches with his general models that he put together a few years ago. And so, dear viewers, dear attendees, that's just the latest in a series of geologic stories that all come from this wonderful Pacific Northwest. We'll never run out of stories to talk about. Some of it's old research involving Mount Stewart coming from Mexico. Some of it's new research involving Mount Baker with a new person that we have in our geology department. And everything in between. Going up to Slate Peak, you can keep going up to Slate Peak and looking at these rocks and banging on them and getting new sets of data from places that have been already figured out, quote unquote. But we know that's not the end of the story. And so this playground is nearby. The geologists continue to crawl all over the place, and you continue to come to these lectures to keep up on what's the latest. Thank you so much for coming to this one and all of these this spring. Thank you, I love you, and goodbye from Ellensburg, Washington, USA.